So today we are going to wrap up week 4. So week 4 we learned about separation of variable and also how to solve exact differential equation and how to use the integrating factor. So one of the application is how solving first order linear differential equation of this form right here. 이건 쓰는 게 안 되는구나. Okay. So when you're looking at this differential equation, this is linear because the derivative of y and the y itself is linearly summed with the coefficient in function of x, and there is a non-homogeneous term. If this is 0, we call this homogeneous equation. When q is 0, we call this homogeneous equation. When q is not 0, then we call this non-homogeneous. So this is a general form of linear differential equation of first order. So first order means that the highest order of derivative is 1. So when you solve this differential equation, you can set your integrating factor nu as e to the integral of px dx, and the solution is the following. So if you look at this formulation, it's very complicated, but you can easily derive this using the same technique we learned in previous lecture. So let's do this. So let's try to write it as a similar form or exact form. So we have dy plus and pxy minus qx dx equals to 0, minus qx, right? So this term will be m, and here's 1 missing here, so this is n. So we want to check, if you go back to the previous slide, what we want to check is the following. Either my minus nx is function of x, or nx minus my over m is function of y. So when you plug in m and n in this case, you can see that my is just px, right? Because there's only one y in the formula. And nx is 0. So this form becomes px over 1, which is the function of x. So this is our direction to choose the integrating factor. How about this one? Just for your information, let's check this case. And this is 0 minus px over pxy minus qx. Now there is x and y, so this is not a function of y only. So this is not the case. So we choose this case. And in this case, our integrating factor is e to the minus of this fraction, which is px. So that's why we had an integrating factor in the theorem. So let's see what happens when I multiply these integrating factor to the equation here. So we have e to the integral px dx dy plus and e to the integral px dx and pxy minus qx dx. I want to find a function f such that this part becomes fy, which is, if you remember, this is a partial differential equation of two variable function f in terms of y, and also I want this to be fx. So let's start from the easy part. So if I start from here, I can guess my two variable function fxy to be this time y, e to the px dx times y plus some function of x, because x is considered to be constant when I take partial derivative of y. So let's say gx here. And if I take the partial derivative of this formula in terms of x, I want to get this result. So if I start from this guess, then fx is e to the minus px dx, the same thing because this is exponential function. And y is considered to be constant. And also I want to take the derivative of exponent, which is px, and the g prime x. So if this formula is equals to this formula, then the first sum end is equal. The second sum end must be g prime. So g prime x must be minus of e to the px dx qx. So what will be the gx? I don't know what p and q are, so I can only conclude that gx is something that comes after I take the integration of this thing. So minus of e to the px dx qx dx. Okay. So combining everything here. So where's minus comes from? So minus py pq, so my. So g. So let's write here. Let's write the conclusion here. So my f of x, y, must be equal to e to the px dx y minus this g part, e to the px dx qx dx. And I'm emphasizing again and again, this is not the solution. This is simply a formula of two variable function f. The solution is the implicit equation of this formula equals to some constant. Okay, so this is our formula. Now let's rewrite this in terms of y as explicit form. So I leave my y on the left hand side and multiply this coefficient to the both side, and e to the minus px dx. And if I move this part to the right hand side, I get integral e to the integral px dx qx dx plus c. Okay. So c is a random constant, any constant. If I have an initial condition, then I can choose a unique c satisfying this initial condition. This is a general solution. So the formula contains p and q, and this is the only thing that we don't know yet in a general formula of the differential equation. So if you have a specific equation, then you can always find a solution. So for example, let's look at this example. We have x cubed y prime plus 3x squared y equals 2 sine x. There's no initial condition. If you want to solve, this is a linear differential equation because this derivative, first order derivative is highest order derivative and is summed with the y, and all the degrees of derivatives of y are 1, and these are linear sums. And this is non-homogeneous linear differential equation because the q part is not 0. However, if you want to use the formula that we derived here, you cannot have a coefficient which is not equals to 1. So we have x cubed as a coefficient of the y prime factor. So you have to divide x cubed on both sides. So you get y prime equals plus 3 over x y sine x x cubed. So this is the starting point to solve this differential equation. So in this case, this is our p and this is our q. And since we already derived this formula with integrating factor, you can simply plug in your p and q in the formula. So y, the solution y is equals to e to the minus p, which is 3 over x dx, times integral of e to the so be careful, there is a negative sign here, but there's no negative sign here. So we simply integrating 3 over x dx. And q is sine x x cubed dx plus c. So when you take the integration, this is ln 3 ln x, right? And do not take plus c here because that doesn't matter in this case. So here, this is considered to be the integrating factor. When you take a multiplication on both sides by integrating factor, you don't have to put the plus sign coming from the indefinite integral of exponent. So don't worry about putting extra constant c here because constant c is here to make the general solution. So leave it like this. And here we have integral of x. So this is also ln x, 3 ln x, and x cubed sine x dx c. So we have one more integral. So here we have 1 over x cubed if you delete e and log. So and this part becomes x cubed, and this will cancel out with denominator. So we simply have sine x. So again, when you take the indefinite integral, the last indefinite integral, don't worry about putting constant c because we have c here already. So this is 1 over x cubed times minus cosine x plus c. C comes after. Okay, plus c. Okay. This is the solution. So we have a long way to go, so let's keep moving. If you have any question, please leave a chat. And this is also another application of solving differential equation using the integrating factor. So suppose that you have a differential equation of this form. dy dx plus pxy equals to qxy alpha. Now this alpha may or may not be 1. So in this case, if alpha is not equals to 1, we call this differential equation a Bernoulli equation. So when you have a Bernoulli equation, this is not a linear equation because we have a degree of y in the non-homogeneous term. Well, this is not even a non-homogeneous term because you have to put y part to the left-hand side, and what comes in the right-hand side will be the function of x only. So in this case, if alpha is not an integer, or specifically not 1, then you have degree of y not equals to the integer. So this is not a linear differential equation. So in this case, you have to substitute your y to the 1 minus alpha to the different intermediate variable, say u, and then make the differential equation into a linear differential equation, first order linear differential equation. So if you substitute u as y to the 1 minus alpha, you can change your differential equation to this form, the form in the below, and you can now solve this equation in the same method that we explained right before. So let's derive this formula and solve this differential equation for the example. So substitution is a standard technique in solving differential equation. So if you study deeper into solving differential equations, substitution is very important, and sometimes it's very artistic how to take a substitution so that you can make your differential equation to a solvable differential equation. So this is just one of the simple example. Now u is y to the 1 minus alpha du dy is equals to 1 minus alpha y minus alpha. So y alpha is equals to 1 minus alpha dy du. Okay. Now let's plug in everything. So dy dx. Okay, so that also have to substitute this part, but pxy equals to qx. So in the slide I used capital P and capital Q. I will use just simply small p and small q. And then y alpha is 1 minus alpha dy du. Okay. I will going to remove y everywhere. So where we at? What we have here? So we have dy. So y is a function of x. So and u is a function of y. So therefore, u is also a function of x, and du dx can be computed as 1 minus alpha dy. Still have this guy. Y minus alpha and dy dx. Confusing. So dy dx. Okay. I think it's better to substitute dy dx instead of y alpha here. So let's not substitute this part. Let's substitute this one. So if I rewrite this dy dx in terms of du dx, what I get is 1 minus alpha 1 and 1 over y alpha y alpha du dx. So plug in this part to the given differential equation. I have y alpha 1 minus alpha and du dx instead of dy dx plus pxy equals to qxy 1 minus alpha. Sorry, just alpha. So now let's divide y alpha on both sides. What we have, and also multiply 1 minus alpha on both sides. Since alpha is not equals to 1, so this is not 0. So this equation now becomes du dx plus 1 minus alpha px and y 1 minus alpha, because I'm taking 1 minus alpha to the denominator, and right hand side qx. Okay, so this guy is simply u. So that's how we get first order differential equation. Here 1 minus alpha 2. First order differential equation, linear differential equation. Then let's look at the example. So our example is when alpha is 3, so given by y prime plus 2 over xy and equals to y cube x square. Yes. So alpha is 3. I'm going to take u as y to the 1 minus 3, which is 1 over y square. You can derive the same, you can just follow the same procedure to get the first order differential equation. But let's plug into the formula that we already have. So when I do substitution, I get u prime plus 1 minus 3. Okay, and what is px? Px was this guy. So 2 over x u equals to what is qx? Qx is 1 over x squared. So 1 over x squared, 1 minus 3. So let's solve this. First, simplify this to u prime minus 4 over x u equals to minus 2 over x squared. Go back to the formula. If you want to solve this once, you can derive your own formula. But if you're going to solve lots of differential equations, it's better to remember the formula. So u is equals to e to the minus of the p. Now this is the new p, which is negative 4 over x. So negative 4 over x dx, and e to the negative 4 over x. There's no negative here. And I'm sorry, so there's another big integral. Big integral of e to the negative 4x dx times q, which is negative 2 over x squared dx plus c. So this is plus. So in integrating, this one is 4 ln x becomes x fourth, and this is integral of 1 over x4 and minus 2 x squared dx plus c. So basically it's x fourth times integral of 2 over x6 dx plus c. So this is 7, 1 over 2 over 7, sorry. 2 over 7 x to the -7. Oh no, 5, sorry. So 5 minus 5 and plus c. So when you simplify this, this is 2 over 5, 1 over x plus c times x fourth. Okay. Now, this is the formula of u. Correct me if my calculation is wrong, because I'm not good at calculation, as you all know by now. So I want to express my solution in terms of y, because the original equation is in terms of y. I want to find solution of y in terms of x. So u is given by 1 over y squared. So the final answer will be y equals to square root of 2 over 5, 1 over x plus c times x fourth. So y could be negative or positive. So it depends on which side you are in. So if you're looking at your initial value at initial point to be the negative, then you put the negative sign here. If it's positive, then you put the positive sign. So plus and minus depend on the initial value. So general solution is only telling you the formula of the solution. If you want to find particular solution, you need the initial condition, or at least one point that this solution curve passes through. And this plus minus sign will be determined by knowing what point you want to you want your solution curve to passing through. Okay. And also you can check that this is a solution by plugging in your formula into the differential equation. So this is one example of first order linear differential equation. Now assume that the level y is a certain hormone level in the blood of a patient at the time t, and suppose that the time rate of change, I think this is a typo, so rate of change, just remove this time word, so just remove this word. The rate of change of the level of hormone is difference between a sinusoidal input of 24-hour period from the thyroid gland given by the function L, which is 1 plus sine omega t. So it fluctuates with the frequency omega, and a continuous removal rate proportional to the level present R t. So the function of removal is given by function R, and this is given by 0.05 y. So it's proportional to the level of y with proportional constant 0.05, which is removed from the blood. Set up a model for the hormone level in the blood and find its general solution. So basically means that write the differential equation and find the solution. And also find the particular solution satisfying the initial condition y0 equals to 0. So at the beginning of time, there is no hormone level, 0 hormone level. Okay, let's look at this one. So basically the questions in the midterm or final are of this kind of form. Some questions will be just find solution by given formula, or other questions are like the word question. You have to set up your own differential equation. So dy dt is the rate of change of hormone level, and there's an input and output from the thyroid and output from the removal by your body, okay? And input is Lx and output is Rx. So LT, sorry. So RT. So LT is given by 1 plus sine omega t, and RT is given by 0.05 y. Okay. So when you move your y to the left-hand side, what you get is y prime plus 0.05 y equals to 1 plus sine omega t. Now, if there's no ambiguity of the independent variable, because we already know that this unit is time or second, so this measures the time, and we're going to take the derivative of in terms of time t, so we're going to omit dt in the equation. And you see this is a linear differential equation, first order linear differential equation. P is 0.05 and Q is this part. So QT and PT. Let's try to solve this. So by formula, so y is equals to e to the negative of pt, which is 0.05 dt, okay, times integral of e to the 0.05 dt times 1 plus sine omega t dt plus c integral parenthesis close. So you can find your solution simply by integrating these indefinite integrals. It's not hard. The only tricky part is integrating the sine omega t times this exponential. Because when you keep doing this, this becomes e to the negative 0.5 t. So this is simple. But however, this part becomes e to the 0.05 t dt plus, so I'm separating this 1 and sine omega t, e to the 0.05 t sine omega t dt. So when you're integrating the integrand obtained by multiplying this exponential and sine, you have to take the substitution, integration by parts twice, and the formula becomes a little bit complicated. I leave it as an exercise in the homework. And this part, I don't think it's hard. You can just simply take the integral. So that was the end of week 4, and so far we did up to chapter 1. Okay, chapter 1 in our textbook, Crazy's Advanced Engineering Mathematics. Any questions? 덥냐? No questions? All right, so let's move on to the week 5. So on the week 5, there's not much calculation. We're going to study the nature of differential equation. So here's the theorem. So the differential equation of this form, dy dx equals to fxy with initial condition, the solution exists if the two-variable function is continuous on a neighborhood of x0 comma y0. So this theorem depends on the knowledge of continuity of two-variable function, and we're not going to talk about the continuity of two-variable function until the multivariable calculus course. So just think about this situation as the directional field is smooth, which means that the arrows on each point smoothly changes as you move your point in two-dimensional plane. Then it says, the Peano theorem says, the solution exists. And this theorem just tells you that the solution exists. It doesn't tell you how many solutions exist. Now the next theorem, Picard-Lindelof theorem, tells you that there is a unique solution if the function f of fxy, which is on the right hand side, and another two-variable function obtained by taking partial derivative of f in terms of y are continuous. So, of course, the Picard-Lindelof theorem is much stronger theorem than the Peano theorem. And I'm not going to go deeper into the proof of this theorem, because checking whether the two-variable function is continuity is not an easy task in general. And understanding the proof of this theorem is not helping to actually solving the differential equation, and understanding the nature of the theorem is not our goal in this lecture. So let me just give an easy example. So when you have y prime equals to x square root of y, and the initial condition is y0 equals to 0. Now this is well-defined differential equation, although you cannot find a solution when the value of y is negative, because we have the square root of y. Now, this is f of xy in two theorems that we mentioned. And when I take the partial derivative of fy, I take x as constant and take a derivative in terms of y. So I get x over 2 times square root of y 1. Okay? And you see, this formula of x and y is not defined when y equals to 0. So this is not defined at 0, 0, because y is 0. And also, if y goes to 0, which means that the denominator becomes 0, then f of y will diverge. I'm assuming that my y is positive, so it approaches to 0 from the right hand side. Then fy, the value of fy, goes to infinity. So this is not continuous. Fy is not continuous around 0, 0. So at x, we have no value assigned for Fy. Around 0, 0 in the two-dimensional plane, Fy is not continuous. However, original F is continuous. However, Fxy is continuous around 0, 0. If you don't like the fact that we're not assuming that y is negative because we have square root of y, just put the absolute value in around y so that this function, this differential equation is defined in the entire plane. Now, let's try to solve this differential equation because this is the type that we can solve by separation of variable. By separation of variable, this square root of y dy equals to x dx. By taking integral, we have y 1 over 2 equals to 1 over 2 x squared plus c. So y 1 over 2 equals to 1 over 4 x squared plus c. I can take this as a c over 2, but c is any constant, so let me just put it as a c again. Therefore, the solution is square of 1 over 4 x squared plus c. So this is the general solution. Now, we have an initial condition that y0 equals to 0. Plug 0 here. I need to get y equals to 0. So 0 plus c squared, right? So c must be 0. So what's the conclusion? The particular solution satisfying this initial condition, initial value problem is 1 over 16 x fourth, because c is 0. Now it tells you that this is a solution, but it doesn't tell you that this is a unique solution. There could be another solution, which is just constant solution. So this doesn't come from the general form of this general solution. If you plug in any value in c, you will not get a constant solution because there is a variable term x. So this y equals to 0 is obviously a solution because if you plug in y equals to 0, where 0 is just constant function, this prime, y prime, is the derivative of constant function, which is 0. And on the right-hand side, square root of 0 is 0, so we have 0. So the differential equation is satisfied. So this is a solution, but we call this a singular solution. And this one, y equals to 1 over 16 x to the fourth, is a particular solution obtained from a general solution. Okay, so we have two solutions. Two solutions both passes through the point 0, 0. So when you draw the directional field of this differential equation, if you want your vector or your solution passes through this origin 0, 0, there are two types of solution. One comes from horizontal line x-axis and keep moving along the horizontal line, and the other comes from the above of x-axis, and then it touches the x-axis at the origin, and then move again to the upper part of x-axis. Now, if you know the initial condition 0, 0, you cannot tell which solution you are looking for. It could be either comes from the horizontal line, x-axis, or it comes from the above x-axis. So you don't have a unique solution. So in this case, this situation itself is called a singular differential equation. So singular means that the answer is not unique. So again, there's no solution curve on the below of x-axis, no solution curve can exist because square root of y is not defined. So you don't find any solution curve passing through the point below x-axis. We only consider the solution curve above x-axis. But in the above of x-axis, there are two solutions at this point. So this is called a singular point. And this initial value problem, abbreviated by IVP, is called singular, or not particularly this initial value problem, just a general initial value problem is called singular if there are two or more solutions. Okay. Okay. Now, in the rest of the class, rest of this semester, we're not going to cover much on singular differential equation. We're going to learn how to find a unique solution in non-singular differential equation, okay? Or non-singular initial value problem. So here's a definition first. So finding a particular solution of nth order differential equation satisfying n equations. One is from y of x0 equals to y0. Here x0 and y0 are just constant. And the second equation is y prime x0 equals to y1. Now y0 and y1 are different values. And the nth order derivative of y at x0 equals to yn. So we have there's a typo, a serious typo. So we have nth order differential equations. So we need to have n equations. So the initial condition runs up to n minus 1th order derivative. So n here. So here, right here, that should be replaced to n minus 1. Okay. 자, 요거 제가 적는 게 안 돼가지고 잠깐만요. 적는 게 안 돼서 그런데 n이 아니고 n-1이에요. 요거 n-1이고 총 n개의 방정식이거든요. n개의 등식이거든요. 그러니까 n-1까지 가야 돼요. So, for example, in the second order linear initial value problem, the initial conditions are two. There are two initial conditions, one for the value of y and one for the value of y prime. So the differential equation itself has y double prime in the equation, but initial condition only up to y prime. Okay, so this is y to the n minus first order derivative of x, or derivative of y at x0. So let's look at the example. So later we are going to learn how to solve the actual solution. Here we are given a solution of second order differential equation y double prime plus y equals to 4x plus 10 times sine x. And if you plug this formula into the differential, I'm sorry, so this one. So sorry for small slide. 방송 되고 있죠? 잘 듣고 있어요? 네, 제가 조그맣게 해놔가지고 잘 안 보였죠? 네, 미안합니다. 잠시만요. So 여기가 오타예요. y의 n차 미분 개수가 yn이라고 되어 있는데 식이 총 n개예요. n개. 지금 0차 미분계수에서 시작해요. 0차 미분계수는 그냥 함수랑 똑같은 거예요. 0차는. 그러니까 함수값에서 그 0차에서 시작해서 n-1차 미분계수까지 여기가 이제 총 n개죠. 그래서 요 n이 n-1이 돼야 돼요. 여기서 n이 n-1이 되고 여기서도 n-1이 돼야 돼요. 그래야 총 n개가 나오죠. 예를 들어서 2개 미분 방정식이다. 그러면은 2개 선형 미분 방정식이다. 그러면 이제 2개 선형 미분 방식이 있고 그 다음에 컨디션이 두 개예요. 하나는 0차 미분계수, 다른 하나는 1차 미분계수 y 프라임. 그렇게 이제 두 개 있어야 돼요. So let's look at example. Initial value, initial point may not be 0. Suppose that we have pi as our initial point, and initial value of y at this pi is given by 0, and the differential, first order differential has 2 as an initial value at pi. So if you want to find a solution, particular solution satisfying these two initial conditions, then plug in pi in x and then set up equals to 0, and then second, take the derivative of this formula and plug in pi to x and equals to 2 to solve x, as to solve SE1 and C2. So basically you have to solve the system of equations, system of just simple equations to find two variables, C1 and C2. So then this is the result. Now, the question is, when does this initial value problem always have a solution? So here's the theorem. If you have a linear differential equation, so this is a linear differential equation right here. All the degree of the derivatives are 1, and it could be homogeneous or non-homogeneous. If this differential equation has initial condition, and now this is the right expression, so we have up to n minus first order derivatives. If you have n initial conditions for each differentials, then it has a unique solution. Okay. Most likely we are going to solve the system in this type, of this type. So we're going to find a unique solution. Let's see, for example, we have y double prime plus y equals to secant x, and initial condition is generally given by x0, comma y0. It has a unique solution if our value x0 lies between minus pi over 2 to pi over 2. Now, secant x is defined if and only if cosine x is 0 and cosine x is 0 at minus pi over 2 and pi over 2, and also rest of the integer addition of these values. However, if x0 is say pi over 2, then this right hand side non-homogeneous term is not defined, and it's actually not continuous. This differential equation does not have solution. You cannot simply find a solution. So you can only change your initial value, initial point within a range of two discontinuous point, and the functions, coefficient function, in this case aix, and non-homogeneous term are continuous in the range. So if you have, so this is the solution that you can solve. If you solve your differential equation using various techniques, you have this general solution. And to find the particular solution, you need two initial conditions. Say you have an initial condition y0 equals to 0 and y prime 0 equals to 1. Then just plug in zeros and set up two equations to solve C1 and C2 to find a particular solution. Now here's the question, here's the important questions. Now we have a solution and I want to draw my solution curve. What's the domain of this solution? What is the domain of definition of the solution curve? How far I can draw my solution. So looking at the solution curve, a solution formula here, because we already have solution. Cosine x is defined on entire real line, right? Sine x is defined on also entire real line, and x sine x also, cosine x also. But here, now let's look at ln of absolute value cosine x. Ln, the log, is defined only at the positive side, right? And now we have absolute value, but the value of cosine x inside of log cannot be 0. If it's 0, then log diverges. So cosine x inside of log can only take a value either bigger than 0 or less than 0. Because we have an absolute value sign, it will be always bigger than 0. So it means that cosine x must be always bigger than 0. Now, if x ranges from minus infinity to infinity, cosine x ranges from minus 1 to 1 and oscillating from minus 1 to 1. And it will cross 0 at some point. So in order to have non-zero value inside of log, my x must be lies inside between minus pi over 2 and pi over 2, or pi over 2 to 3 pi over 2, and so on. So there is a range of definition of solution curve depend on the existence of solution. So you have a unique solution if and only if my initial point lies between minus pi over 2 to pi over 2, right? Any value between these in this interval can be used as an initial point. That means if I choose any point in between in this interval, I will have a smooth curve near that point as a solution curve of this differential equation. So this interval can be used as a domain of definition of solution curve. Why this is important? Before you actually find your particular formula of solution curve, you can find the definition of the domain of definition of your solution curve without knowing specific formula of solution curve. Without knowing that this is the solution of differential equation, y double prime plus y equals to secant x, I know right I know from this point by looking at the differential equation that the solution curve will have a domain of definition in between some interval where the secant x is well defined. So let me write this in the blackboard because at some point we'll be confused. So we have an, yn to a1. So these are not just constant. These are function of x. An x. Sorry. Yeah. An x and y prime plus a0x y equals to fx. Let me write it as a theorem. The interval of domain of the solution of this differential equation is the same interval of domain of a1x to a0x and f of x, where these functions are differentiable. So, for example, let me give a slightly different example. Suppose that we have y double prime plus 1 over x y equals to, let's say, tangent x. Okay? And I want to find a particular solution at y pi over 4 equals to 1. Okay? Now, it means that if I find a solution, then it will pass through the point in the plane given by pi over 4, 1. So it will be like this formula. And this. Where's the domain of interval? How far I can draw this curve? Now looking at the coefficient functions. So this is a0x and this is fx. This function 1 over x defined on the interval which not contains 0. So as long as x is not 0, this is well defined. So this domain of interval is minus infinity to 0 and 0 infinity. Now how about tangent x? So basically if cosine x is not 0, this is well defined. So this is infinite union of intervals from minus infinity to minus 3 pi over 2 to minus pi over 2, minus pi over 2, pi over 2, and so on. Pi over 2, 3 pi over 2, and so on. Now, I have my initial point lying at this interval for the domain of interval of tangent x and also this interval. If you want to find an entire domain of interval of solution curve, the interval of domain of solution curve should be the intersection of these two intervals. I cannot go. My point of integration. My solution curve cannot pass through this pi over 2. This is the end of my interval domain of this non-homogeneous term. And also I cannot pass I cannot pass below than 0 because 0 to infinity is the one of the interval of domain of this coefficient function. I cannot pass through 0. So 0 to pi over 2 is the interval of domain of the solution to this initial value problem. Okay. If I'm trying to solve a general solution, there's no meaning of finding domain of interval because I don't know which particular function I'm looking at. But if you're trying to find initial value problem, you're looking at a specific function, and every function must have a domain, in this case domain of interval. And without specifically find a formula for solution, I know that this solution must be the solution curve must be lying between 0 and pi over 2. So which means that function is not defined at 0, so either it diverges to negative infinity or positive infinity. So I can guess that this solution curve will be have an asymptotic line at 0 and also at another asymptotic line at pi over 2. I don't know whether it goes to above or below, but anyway, I know that the solution curve only lies between 0 and pi over 2. So it's very important to understand this nature of differential equation because it's more important than memorizing the technique of solving differential equation, because later there are many tools and many methods of finding solution curve, and most of the differential equations cannot be solved by hand. So basically you have to guess numerically the solutions. But when you guess your solution, it's important to know the geometrical picture of the solution curve and nature of solution curve before you find your solution. If the differential equation is very complicated, you need lots of computing powers, and it will take lots of time before you obtain an actual solution. But if you know what the nature of the solution should be, then you can do your research on this differential equation, and that will help. And here's the let me check the time. So what time is it? So it's 11:11. So almost an hour passed. Okay, let's do this. So we have a boundary value problem. So it's different from the initial value problem. So what is the boundary value problem? Finding a particular solution of nth order differential equation satisfying. So this is also a typo. This is up to n minus 1. Okay, so this is also up to n minus 1. Is called a boundary value problem. So you see there is n equations starting from x0 to xn minus 1. This is a typo in the slide. And there's no equation in terms of differential of y. So it only constraints on it. These are the constraints on the value of the solution. Okay. And only difference is that we're not measuring the value of y at the same point. The points of value of y are all different. We have x0 to x1 and up to xn minus 1. So at the different point, I want my solution passes through the value of y as y0 to yn minus 1. So finding a solution satisfying this equation is called the boundary value problem. boundary value problem, you may not have a solution. So there are two different, the boundary value problem and initial value problems are very different in the sense that initial value problem has, with some condition, has a unique solution. Boundary value problem have no condition that you have a unique solution in general. Boundary value problem can have no solution. For example, let's look at this one. Y double prime plus 16y have a general solution, C1 times cosine 4x and C2 times sine 4x. If you plug in this equation to this differential equation, you can check that the left-hand side identically becomes 0. Now, let's look at three types of boundary value problem. So first one is y0 equals to 0 and y pi over 2 equals to 0. So let me just go back to the blackboard. So all three conditions measures the value of y at x equals to 0 and x equals to pi over 2. Now the first one tells you that I want my solution to pass this through 0, 0 and pi over 2, 0. There are solutions of this form because you can take your sine function, sine 4x, with some constant c, well in this case c2, right? Here the c2 is the amplitude of this sinusoidal curve, will satisfy this boundary value problem. It's 0 at x equals to 0 and also 0 at x equals to pi over 2. However, I can take any amplitude to satisfy this boundary value problem. So there are infinitely many solutions. It can be small amplitude, it can be big amplitude sinusoidal curve, and there are infinitely many solutions. However, the second condition, we have y 0, 0 and pi over 8 is also equals to 0. There are no solutions satisfying this condition. If you plug in 0 and pi over 8 into the formula and set up two system of equations, C1, C2 becomes all 0. So let's check that. So when x in here, if I plug in this condition, I get C1 times cosine 0 plus C2 times sine 0 must be equals to 0. So this 0 is the value of x and this 0 is value of y. Okay? So just distinguish them by color. Blue is x and red is y. And how about the second condition? So in the second condition, C1 cosine pi over 8 and C2 sine pi over 8 is equals to 0. I'm sorry, so it's 4 times x, so it's 2. Okay. So now sine 0 is 0, which means that this equation says C1 is 0. And how about cosine pi over 2? This is 0. So sine pi over 2 is 1. So this second equation says C2 is 0. And C1, C2 is 0. And this is a solution. It's not a solution in terms of x, but it's still constant solution. So we have a solution, one solution, unique solution. But in the second equation, third condition, we have boundary condition 0, 0 and pi, so it should pass through pi over 2, 1 here. So it says there is no solution satisfying these conditions. So I cannot draw my solution curve in terms of in the form of C1 cosine 4x plus C2 sine 4x, satisfying these conditions. To check that, you can simply plug in your values here. C1 cosine 0, C2 sine 0 is 0, and C1 4 times x, so it's 2x, 2 pi, plus C2 sine 2 pi equals to 1. Now, the first equation tells you that the C1 is 0. How about the second one? So second one also, this part is 0, so it tells you that C1 is 1. So it's sort of contradicting two equations. So there's no solution satisfying these conditions. So in the boundary value problems, you have to be careful setting up the differential equation. If there's no solution, your model is wrong. You cannot model the system by an equation which has no solutions. Okay? So the initial value problem, you can simply find your differential or set up the differential equation from the hypothesis, knowing that there is a solution. However, in the boundary value problems, the modeling is a lot harder because the solution may not exist. Okay, so I think this is almost the end of our class. So in the rest of sections, we have MATLAB recitation. So while I'm preparing the MATLAB, please ask any questions. 질문 있으면 해주세요. MATLAB 준비할 동안에. 없으세요? Okay, so in this 아이고 뭐 어떤 거야? So today we are going to practice the finding solution of differential equation using MATLAB. Okay, so solving numerically using ODE 45. So if you search for how to solve differential equations using MATLAB, there are many tools in MATLAB. ODE 45 is only one of them. And how to use it is, first you have to set up your differential equation of this form: y prime equals to fxy. Okay. So basically we start from the first order differential equation, and the function fxy, the two variable function, is defined as an anonymous function. Let's start from the equations that we started from. So here in the lecture 4, okay, let's start from the example. So this example. This one. We have omega as a symbol, so let's say omega is a 24-hour period, so it's 1/24, where t is the unit of hour. So let's try to do that. So y prime is given by 1 plus the input, 24, and output is given by 0.05 times y, right? Yes, y. Okay. Sorry, this should be t, not x. Okay. 됐죠? 미안합니다. So this is the input and this is output. And when you use the ODE45, the output is the range of x coordinate and y coordinates, the array of x coordinates and y coordinates. And we have to take that in another array, another symbol, to actually plot the graph. So although I use t and y as a variable of this function, this t and y is only used in this context. So up to this point, t and y are not saved as a variable in the MATLAB. So I'm going to use t and y as the variable for saving the array of values of solution curve obtained by ODE45 command. So it says, well, in the online MATLAB, it tells you how to use this command. So first you put the ODE function, which is the fxy part, and tspan, which is the array of t, and y0 is the initial value, not the initial point, initial value of this solution y. So we have initially 0 level of Hermann. So first f, and tspan is the interval of integration, let's say 0 to 24 hours. So, and then y0 initially 0. Let's run this. Run. And in the workspace, if you're looking at the workspace after running this command, you have a variable ty defined as 65 times 1 double. So basically it's a vector of 65 elements and same size of y. Y has the same size array. I think 65 is default. You can make your tspan as arbitrarily long. Let's say I want my 0 to 24 equally spaced by 100 points. Then I have 100 times 1 double. So if you want your solution curve to be plotted in a larger number of points, then you can make a linspace as span, and you can increase the number of elements in the array by increasing this number. So if the default is 100, you can make it as 1,000 or 10,000. Now let's plot this t and y. Okay, so it says t. Sorry, t. 잠깐만요. 24-hour, 2 pi. Sorry, so I should multiply the period of the sine, 2 pi. So you see, 아직 잘 안 보일 텐데 이쪽으로 조금 보이죠? You see the sine. It's not sine. It's first increasing. The graph reaches to 15. 15 is the level of hormone, and then it decreases by the decreased rate of the sine rate of the what's the hormone by thyroid, and then increase by increase input rate of the hormone from the thyroid. If you want to plot this graph for larger period larger domain, let's just increase that into t's. Okay, so t is a unit of hour. Yes, unit of hour. So if I put 0 to 24, it only lasts for 1 day. If I multiply by 10, it's a 10-day period. Now this is the picture that you might see in the textbook. So it first increases. This is the x-axis is a unit of hours, and increases, and basically it will eventually behave like a sinusoidal curve, because at some point at the beginning there's no hormone at all, so the increase rate will dominate, and then the level of hormone increases. But later the increase and decrease by the body, decrease rate comes from the removal of the hormone from your body, will be eventually saturated. So increasing and decreasing will be harmonized. So you will have a well-balanced increasing and decreasing of hormone. If you keep going, if you keep moving your time period to 100 days, you see the fluctuation will not change. It's almost equal. Similar figure after around 5 days or 2 days. Okay. Let's do other things. We had, okay, so in the week 5, today we had example of this one. Yeah, we had this example, and let's check the solution of initial value condition at pi. Okay, we had a specific solution, but I just want to graph it without actually finding the solution by hand. So remember that formula, and let me rewrite that in here. So y double prime plus y equals to 4x plus 10 sine x. Okay, and initial condition y pi equals to 0 and y prime pi equals to 2. So what is my function y? So that has to be minus y plus 4 times x plus 10 times sine x. Okay, because So this is second order. Sorry, second order differential equation, a little bit harder. Um, hmm. So you can solve second order differential equation using the ODE 45, but you need a little bit more of work. Well, let's do this. Do we have time? 10 minutes or so. So, solving second order DE numerically. Okay. So you have second order differential equation. You need to have initial condition. Now, separate second order DE into the system of two first order DE. That's the first step, which means that I take y1 equals to y and y2 equals to y prime. So, and then I will denote as y, but y is now y1 and y, it's an array of function y1 and y2. Okay, basically I want to find my y1 because that's the y. Well, maybe if it's confusing, then let's say this is big Y. Okay, so I want to find the small y, and small y is set up as y1 for convenience, just for now, and y prime is considered as y2, and I want to find the array of function which is y1 and y2, consists of y1 and y2. Then I have y2 equals to y1 prime. That's the first differential equation. And another equation is y1 y2 prime equals to minus y1 plus 4x plus sine 10 sine x. So you see these are two, sorry, y1 prime is y2. Let's make it opposite way. These are two first order differential equation, right? But you see this is a system of ordinary differential equations. In the first week, we had some example of system of differential equation, an epidemic model like SIR model. This is one of the other example that you can call it as a system of ODE functions. And now you see this y1 and y2 prime is considered as large Y prime, which is simply taking a differential on each element of array. So what I'm trying to do is find the first order differential equation to solve this second order differential equation. So I changed my second order differential equation as a first order differential equation, but the difference is that this is a single differential equation, but this equation consists of two differential equations. So it's a system of differential equations. So this is y2 and minus y1 plus 4x plus 10 sine x. So this is a setup. This is background. And I want this part to be a function, in this case large f, function of x and y. Here y is a function of y1 and y2, so large Y. Let's redefine this. So f is second order two variable function, x and large Y. But now I don't want to use large Y because I don't want to define. I'm not going to use another symbol here. instead of large y is consists of two variables, y1 and y2. So first, so y2 is the y2 right here. Okay, so y2 here. And then minus y1 plus 4 times x is just small x, plus 10 times sine x. And this is it. And let's try to solve this using the same ODE 45, and I'm putting large f as a two variable function. Span, the span of x is in this case, I'm trying to find the initial value problem from pi. Let's start from pi to, let's say, 3 pi. And I have to put the initial value. So initial value consists of two values, which is one from value of y and the other from y prime. But I set my y1 to be y and y2 to be y prime. So initial value of y1 is the initial value of y, initial value of y2 is the initial value of y prime. So one is 0, this one is 0, initial value is 0, and this one is 2. So the initial value of large y is nothing but the array of 0 and 2. Okay, so, and then I'm going to plot my function. So the result, let me see the result first. Let's see the result before plotting anything. So if you're looking at the workspace, now y, large y, the small y is the previous example. Large y consists of 100 times 2 double array. So this is a matrix of 100 rows and 2 columns. Now there's 2 columns. 100 is simply because I set my x array as 100 array consists of 100 values from pi to 3 pi. I can make it to larger values, so I get 1,000 arrays, 1,000 elements array. However, the large y, the result of ODE 45, has 2 columns. The first column is the value of y1. Second column is the value of y2, right? I don't want the value of y2 because that means it will give the value of y prime. I want the value of y to draw the graph of y. If I use y2 to graph the function, then I'm graphing the graph of y prime. Okay, so when I plot the function x axis is just x, and I need to use the first column of this matrix. How do you choose the first column? This is done by this method. You have large y is a matrix. I'm choosing all row by putting colon here, and then comma comes comma, and then comes the index of column. So I'm choosing the first column. So this colon means I'm choosing all rows. So basically I'm choosing the entries from all rows and first column. So I get the first column entries. So this is the figure. This is the graph of the solution. So when you solve this differential equation at initial condition of at pi, that will have this solution curve. And then initially it starts from 0, and the scale is different from y scale, so it may not see directly. It may see directly, but the slope is almost 2. So let me enlarge this. by taking the range, domain of interval from pi to pi plus 0.5. Okay, see, it's the slope. Well, let me just x is equal. Make the two axes of this be equal. So at 3.1 you have a curve passing through 0 and the 2. So now I scale to be equal on putting x is equal command. So you see the slope is 2, which is the condition. Y prime pi equals to 2. Now the ODE45 only gives the graph starting from the initial point. How do you use your ODE45 to draw the curve before the initial condition? Suppose that I want to draw this function from 0 to 2 pi, but my initial condition is given at the point pi. How do you draw that? So you have to draw the curve, two curves, one starting from pi to plus infinity, and the other from starting from pi to negative infinity. That requires plotting two functions in the same figure, and we will do that in the next time. So from now on, we are going to exercise plotting the numerical solution of differential equation using MATLAB. And if you remember how to draw the solution curve by MATLAB after this semester is over, that's the half of success. Without remembering all the details of solving differential equation by hand, if you simply remember how to use MATLAB to solve numerical solution, then that's okay. That's more important than remembering the finding solution by hand. So thank you for listening. If you have any questions, leave a chat and see you on Thursday.